What? Oh.
Hello everyone. I hope I'm audible now. Mic was on mute. Um, am I audible? Okay, fine. So we'll start the lecture now. So in today's class, we'll be discussing on probability. Uh, we'll start with probability. We'll see random variables, random process, and some concepts in probability. And then we'll move on to statistics. We'll see why we need to study both probability and statistics in data science point of view. All right, so I hope at least some of you have watched the videos in this website. So let's start the class now. So why we need probability, first of all? Because we are discussing about data, like data collections from different sources, but we don't know with what confidence that data is the correct one. So there can be errors associated with the data, so which can be human errors, or like when someone records the data, they might have entered a wrong value, and all such errors can occur. And even the device which we use to measure the data or any sensors, that also can have errors. So considering all those things, uh, we use these probability and the concepts in that to see how we can quantify these uncertainties, so that once we formulate or once we have the data, we can get a meaningful distribution from the data. So starting off, what is a random phenomenon? So random phenomenon or experiment um, whose are those processes whose outcomes are not predictable with certainty. So let's say we can, so if we take a sample, so let's say um, they are rolling a dice, So we cannot be certain that a particular number will come on every trial, right? So whenever we roll a dice, so the outcome can range from 1 to 6. And the probability, if the die is a fair die, if there is no unbiased or anything in the die, we can say that the probability of getting any number that is from 1 to 6 is the same. So we define a sample space for a random phenomena which denotes all possible outcomes of an experiment. So in the example of rolling a die, we can get any of the number like 1, 2, 3, 4, 5, or 6. So any number from 1 to 6 is the output. Now if we uh, make a die like a, so we cannot make a four-face die. So let's say we have an die with yeah, we can make a four-face die. So let's say we have a we join three triangles. Sorry, make four. So if we join four triangles and we make a die, so we can mark the faces by 1, 2, 3, and the bottom face, let it be 4. Then if such a die is used in our experiment, we can get the outcome as or the sample space as 1, 2, 3, 4. So this is the definition of sample space. That is, sample space denotes all the outcomes of an experiment. Now coming to the event. So in a probability, event can be any subset of sample space. So let's say in one experiment or one event, we define it as um, outcome is greater than 3. So in that case, we can have only these three elements, 4, 5, and 6. And another event can be only even numbers. So we will have 2, 4, and 6. So the number of elements in the event can be 0 also. So let's say, so if someone says they want an outcome that is greater than 6 when we are rolling a die with 6 faces. So in that case, the subset will be a null subspace, or the subset of the sample space will be null, because there are no elements in such an experiment where we get 7 or 8 as an output when the die has only 1 to 6. And even the whole sample space can be an event. So if the event is like any number when rolling a die, so that is also an event. So the entire subspace can also be an event. Now probability. So now we have mentioned, or now we have seen event and sample space. So probability is a measure that assign real value to every outcome of a random phenomena. So in our previous example, we have seen that the event of getting gray numbers greater than 3 was had 3 elements, that is 4, 5, and 6, whereas the sample space had 1, 2, 3, 4, 5, 6. So 6 elements were there in the sample space. Now, the frequentist approach of calculating the probability is like count the number of elements in the event divided by the number of elements in the sample space. So it's like now in this case, it will be 3 by 6, which will be equal to 0.5 or half, 50%, whatever we can call. So in the frequentist approach, the normal idea is like, so let's say we have a coin and we want to see what is the probability of getting a head. We do the experiment a number of times, and so let's say we do the experiment for 1,000 times. So if you do, or if you flip a coin if we flip a coin for 1,000 times, we can see that approximately 500 times we'll get tail and 500 times we'll get head. So that's how we reach the conclusion that the probability of getting head when tossing a coin is 1 by 2. And it's the same for getting a tail also. So it's 1 by 2. So the probability is the ratio of number of ways an event can happen to a number of ways the sample space can happen. So in these examples that we have seen, we can actually count the number, right? So let's say the number of samples event is 4, 5, 6. We can count it. Whereas in case of this probability where the total sample space is also countable. So now let's say we have a number line. So let's say from 0 to 1. So 0 to 1 is the number line, and we say that so cut the number at any one point between the number line. So let's say I cut here. So let's say I want to get 0.5. So my event is 0.5. So we have only one element in that case. But if you look at the sample space of this line, we cannot really estimate the number of elements in the sample space. Why? Because this is a real number line. So there can be infinite number of positions where I can cut. Right. So if we look at the frequentist approach of calculating the probability in such cases where the number or the outcomes in the sample space is not countable. So if you look at here, so what we wanted was 0.5, and the sample space is kind of huge. So let's say it is infinity, and in the numerator we have only one element. So the probability, it will be approximately equal to 0. Anything divided by infinity will go to 0. But that is not the case, right? Because we know that the 0.5 is somewhere between this 0 and 1. So there should be some value. So in such cases, usually what we do is we cannot estimate the probability in this approach. So what we can do instead is we will define a upper and lower limit. So let's say this is the number line. So if this is 0 to 1, and we can find the probability of this small cutout from the number line. So let's say this is 0.4, then this is 0.6. In such cases, we can say that the probability of the number falling between these two values can be found. So if you look at the denominator, we put it 1, and the numerator we can say it is in this interval. So we'll get 0.2 as the answer or the probability. So this is the continuous formulation, and we have the deterministic formulation where we are certain about the number that we can get, and we have the continuous formulation. Now coming to the axioms of probability. So probability is always non-negative and less than 1, because the number of elements in the event, the maximum number of element in an event is the number of elements in the sample space. Even in continuous case, the maximum is this limit. So it will not go beyond the limit. So the probability is always between 0 and 1. Then probability of the entire sample space is 1. So if you say like what is the probability of getting any number from 1 to 6, or if the event is like I need to get any number from 1 to 6. So what will be the event in such case? So it will be equal to the sample space, right? So the event and sample space are equal, so that the probability will be like 6 by 6, that will be equal to 1. Then if two events are mutually exclusive, so like we want to find, let's say, what is actually mutually exclusive event. First, let us define that. In 1 minute. Let's see what is mutually exclusive events. So mutually exclusive events like so let's say we are rolling a die. We again take that example. Then what is the uh, chance that, or the probability that one can occur at the same time as the other can occur? So let's say I want to get a number 3, and let's say we have two events, let's say A and B. So A is the event roll A3, and B is the event roll A5. So in this case, if the event A occurs, then B cannot occur, right? So it's like if I roll a die and I get a 3, then there is no chance that the event B can occur, that is getting a 5. Whereas if my events were like, let's say C and D, so C is the event of even numbers. So it's 2, 4, 6. And D is the event of getting like, let's say, numbers higher than 3. So it's 4, 5, 6. So if you look at these two examples, yeah, Mitesh, you have some doubt? Okay. So these are the examples C and D. C and D are two events. So in this case, let's say I got number 4. So both the events are occurring at the same time, right? So the number 4 is present in event C, which is the number of, or which is the even number event, and D is the event of getting a number greater than 3. So in this case, both the number 4 and number 6, or 6 is also there in both the sets. So we cannot say these two are mutually exclusive. Now, two events are mutually exclusive only if they don't have any common elements. So let's if you take the intersection of the two events. So if in here, if you take A intersection B, we will get a null set. Whereas here, if you take PC intersection D, the elements will be 4 and 6. So this is not mutually exclusive, whereas this is mutually exclusive. Okay. So now for a mutually exclusive event, we have this formula: P of A union B is equal to P of A plus P of B. Okay. And this actually comes from the big formula, that is P of A union B is equal to A union B is equal to P of A plus P of B minus P of A intersection B. In this case, this is 0. In terms of mutually exclusive event, this is equal to 0, so that the equation will be P of A union B is equal to P of A plus P of B. So mutually exclusive should not be confused with the independent event. So, independent event are those events like in which the occurrence of one does not affect the probability of the other. Okay, so like we will see the examples when we see what is an independent event. So now we'll have some question. Okay, so yeah, somebody can unmute and speak if these are very basic questions.
So 1/3.
So the answer for, yeah, it's 1/3. And so if two fair coins are flipped, what is the probability of getting exactly one head?
The second one 1/4.
1/4 how? Can you just tell me the uh, elements in the event?
So head for the first coin, head for the second coin, tail, and then 4 combinations like that. So total sample space 8, like that I evaluated.
Total sample space is 8. How
One
is
by
8? So first let's write the total sample space. So we have 2 coins. Okay. So first coin can be hit, second coin can be hit. Then first coin can be hit, second coin can be tail. Then we have tail hit. Then we have tail. So how is it 8? It's only 4, right? So
Yeah, I
elements in
got it, sir.
total sample space is 4. So yeah, somebody has answered it as 1/2. So 1/2 is the correct answer. And in the event we will have 2, that is HT and TH. All right. So this was not 1/3, right? It was 1/2. Sorry. Okay. So here are the explanations. So you can see that 1/2 and 1/2, both are 1/2. Okay. Now one more question for you to that.
1/4.
A is 1/4. How is 1/4?
So 1/2.
Yeah, A is 1/2. And question number 2.
By 56.
Which one?
B option.
Yeah, B is the correct one. So the first question is pretty straightforward. So we have, so it's like number of red is 13 diamond cards and 13 um, hearts. So it is 26 and total number of cards is 52. So we get 1/2. And for the second question, the flow is like this. So the bag contains 5 red balls and 3 green balls. So it is given. First, we have drawn a red ball. So first, we need to find the probability of red. So that is in the total 8. There are 5 reds. So it's 5 by 8. Now, since one ball is drawn, the number of balls has decreased from yeah, Mitesh. So number of balls has decreased from 8 to 7. So now we have 7 balls, and in that 7 balls, the 3 is still green. So we have 3. Just multiplying both will give 15 by 6. Okay. So one more question.
So 1 by 4.
Yeah, 1 by 4 is the correct answer. So in this question, the event is like, so we have a 4-letter word, and the event is that the B is fixed in the first position. Now we want to see how many such words can be formed. So here we can give any 3 letters, that is I, D, and R. So if we give any 3 letters here, so we can give it in 3 number of ways. And if we fix one letter in the second position, the third position will have another 2 letters. Then in the last, we'll have the leftover letter. So the total number of events is 3 into 2 into 1. Whereas for the sample space, we'll have uh, 4 additional. So we'll have any 4 can be given here. Then we have 3, 2, 1. So it will be 4 factorial. That is 4 into 3 into 2 into 1. So the final probability is 3 factorial by 4 factorial, which will be equal to 1 by 4. Okay. All right. So the mutually exclusive events, which we have already discussed. So again, as a formal definition, the occurrence of one event implies that the other event does not occur. So that is the mutually exclusive event. So like we have discussed. So now let's see what is independent event. So independent events are such events that in which if occurrence of one event does not have any influence on the other, like the probability does not changes. Um, so somebody is asking when is the last date for applying exam. Actually, I don't know. You will have to um, ask the Swayam or NPTEL. I'm not very sure about that. Ashrita. So then Mitesh is having some doubt in. doubt in previous topic. So what was the topic? Can you unmute and speak? Then we can. Mitesh Raja. Okay. We'll continue with the class. So the independent event. So two events are independent if the occurrence of one has no influence on the other. So like the two events can be landing on heads after tossing a coin and rolling a 5 on a single six-sided die. So those two events are independent events because if you toss a coin and if you roll a die, the one does not affect the other unless they collide each other or something. All right. So in such cases, this I think this should be negative. Okay, so P of A plus B minus. So this should be this is negative. Sorry. Okay. Okay. So let's see our ball example. So in this case, so let's try to clarify what is independent event. So Havani has typed last date was 11th August for applying for exam. Maybe you will have to see in the SWAYAM or NPTEL site. I don't know exactly when you have to submit for that. Okay, so let's take this example: five red ball and three green ball. So let's see how we can explain dependence with that example. So in our question, it was given we have five red ball, three green ball. Okay, now the first event is like we are taking a red ball, then we are taking another ball without replacement. So that in the question we got the probability first was 5 by 8, and to get the next one, that is the next the green ball, the probability was 3 by 7. Now let's say we have five red ball and three green ball, and this time we are replacing the ball. That is once we take a ball, let's say we take a ball from the basket. So in this case, we are taking a ball from the basket. Then again, we are taking another ball from the basket. But in this case, we are taking a ball from the basket, then we are putting it back. And after that, we are taking the ball. Okay. So in this case, let's say the probability of getting red was 5 by 8. So it didn't change. Whereas the probability of getting green changed from 3 by 7 to 3 by 8. Okay, so if we do with replacement, the probabilities will not change. So let's see again in this example. First we are taking, so here it was red and green. Here it was red and green, green. This is with replacement. So with the replacement, here it was without replacement. Okay, so now let's see first we are taking green ball, then again we are taking green ball. So this is without replacement. So first probability will be 3 by 8. And next the probability will be 2 by 7. Because already one green ball is out and we are not replacing. Whereas let's say with replacement, we are taking green ball. So that what will be the first probability? It's 3 by 8. And we are again putting the ball back to the box. So again, in the box, there are 8 balls and there are 3 green balls. So again, the probability will remain the same, 3 by 8. So in this case, the events are independent, or the probability is not affected when the balls are replaced. Whereas in the first case, the probabilities was affected. All right. Now to explain all these things, we use Venn diagrams. So Venn diagrams are like an easy graphical representation of different kinds of events. So we can see different Venn diagrams here. So A union B means the elements or the occurrence of both the events combined. So it can be like in our previous example, we have seen that. So let's take that example itself. A is even number, so 2, 4, 6. Then B 4, 5, 6. So it is even numbers and greater than 3. So greater than 3, then even numbers. So for the first case, A union B, it will be the combination of all the elements in the event. So if we draw the Venn diagram for that event, so we have A, then we have B here. So A will have 2, 4, 6. So we have 2, 4, and 6 are available in both. So and B have 5. So A union B will have all the elements, that is 2, 4, 5, and 6. Whereas A intersection B will have 4 and 6. So A union B will have 2, 4, 5, 6. Then A intersection B will have 4 and 6. Now I don't know what this is actually called, maybe difference or something. So this is A union B minus A intersection B. So that will have the elements 2 and 5, because the common elements are not present in this configuration. Then A complement are, so we also have other elements, right? Like we have 1 and 3. So let's say 3. So this entire block represents the sample space, the rectangle. Then we have different events inside that. Okay, so now A complement is everything other than that is present in A. So what will be A complement? So in this case, A complement will be 1, 3, and 5. So just by Venn diagram, we can see that it's 1, 3, and 5. So whatever outside A will be in A complement. Then similarly, so A intersection B complement. So that will be the elements. A intersection B complement will be the elements that are only exclusive to A. So that will have only one element, that is 2. Then similarly, A complement intersection B will have element exclusive to B. And the last row, so we have A union B complement. So that will have all other elements which are not exclusive to B. So we have we'll have 1, 2, 3, 4, and 6. And now we have A complement union B complement. So it's like combining the elements which are not common to both A and B. So if you see this one and this one, hi Mitesh. Mitesh is again. So Mitesh, I will type my
Sir, we can take odd numbers, no, sir.
what?
No, sir, in this Venn diagram, we can take odd numbers, no, sir.
I can't hear you. Can you please talk loud?
Sir, we can apply the odd numbers, no, sir, in this Venn diagram.
What can you apply?
Odd numbers, sir, in this Venn diagram.
Odd numbers.
Yes, sir. For example, like 3, 5, 7, 9, like that numbers.
But in this case, we have two events. So one event is even numbers. And the second event is only numbers greater than 3. Now, if you want, let's say, if you define another event C, odd numbers. So odd numbers. So that will have 1, 3, and 5. So we will have to draw another. So it's kind of difficult to draw. So let's say we put 1 here. Then we can draw here. So this is the event C. So this is not 1. Okay. So we can draw different events.
Okay, sir.
We can draw any number of events if it is defined. So first we had defined only 2 events A and B. So that was shown in the Venn diagram. Now, since we have increase the number of events, so we can show that also. So,
Okay,
so as I was saying, so if you look at these two, the second column, first row and last row. So can you say if this is mutually exclusive or independent events? What can you say about that? Mhm. So by looking at the Venn diagram itself, we can say that these two events are mutually exclusive. That is A intersection B and A intersection B complement. So these two events are mutually exclusive. So we can say one more thing. So if you have an event, let's say we have an event A, then A comma will be always exclusive to that event, mutually exclusive to that event. And if you see, if you combine these two events, so if you combine these two, finally, if you draw the Venn diagram, so I have no space to draw. Okay. So if we draw the Venn diagram, and if you combine the colors, so we are going to get a complete sample space is covered. So such events are called mutually exclusive and exhaustive events. That is, if two events are mutually exclusive and exhaustive, so those two events cannot occur together, and at least one of them must occur, right? So let's say, so let's take this Venn diagram. Okay. So in this Venn diagram, As you can see in our example, this one had 2 and 5. So even though it is mutually exclusive, and if we roll a die, and if we get number 1 on the die face, that is not present in either of these events, 2 and 5. It's not 2, it's not 5, so it's not present in this Venn diagram. So it is not exclusive, not exhaustive. It's mutually exclusive, but not exhaustive. To be exhaustive, so once we combine these two, so if you combine this one and this one, so this one had the events 4, 6. So this one had 2, 5, 1, 3. Now, if you roll a die, and we are sure that the combination of this event and this event, these two events are mutually exclusive, because getting 4 and 6 are exclusive to this event, and getting 1, 2, 5, 3 is exclusive to this event. And also, if you roll a die and any number comes up, it will be present in any of these two events. So such events are called exclusive events, exhaustive events. Sorry, so one property of exhaustive
Come
events
again,
is
sir.
like,
We repeat this point.
okay,
Exhaustive one.
so
Come repeat again.
okay, exhaustive events. So let's take a simple example of calling tossing a die. So if you toss a die, toss a coin, let's toss a coin, then there is only two outcomes, that is a head or tail. Okay, so getting a head and getting a tail is our 1 minute. So getting a head, getting a tail. So this is our entire sample space. So it is either head or tail. Okay. Now, if head can occur, then tail cannot occur. So that it makes these events, like event of getting a head and event of getting a tail, as mutually exclusive. That is, if head occurs, tail cannot occur. So that is confirmed. Now, while tossing a coin, only head or tail can occur. Or if we combine these events, so let's say event 1 is getting a head, and event 2 is getting a tail. So if we toss a coin, either we will get head or we will get tail. Now, if we combine these two events, and if we toss a coin, we are sure that either E1 or E2 will occur. Whereas, so let's say we are taking, we are rolling a die, then we have the same thing, let's say 2, then 5, let's say this is, so 2, 4, 6, then this is 5, 1, 3. So we have three A, B, and C. So A is the event of getting even numbers. Then B is a number greater than 3. Then C is odd numbers. Okay. Now, so actually this will cover the entire sample space. So yeah, let's see. So there are no elements outside these things. So this will be the entire sample space. 1, 2, 3, 4, 5, 6. Now what we are, so let me draw it clearly. So A, B, C. So this is A. This is B. So this is B. Then we and this is C. There will be here. Then we have C and okay. So this is A, this is B, this is C. So A is even, so it has 2, 4, and 6. Then B is greater than 3, so it will have 4, 6, and 5. Then C is odd, so it will have 5, 1, and 3. Now we say that um, if we see B and if we take event A and B, so these are not mutually exclusive because there are common elements in both, so that the occurrence of A will have elements in B. Now let's take A and C. Okay, so when we take A and C, so A and C, A has elements 2, 4, 6. Then C has elements 1, 3, 5. Now if we combine A and C, we get the entire sample space. Also, we can see that there are no common elements in A and C. So since there are no common elements in A and C, that makes it mutually exclusive. And on combining A and C, we get the entire sample space. So that makes it mutually exhaustive, mutually exclusive and exhaustive.
Understood, sir.
Okay,
Thank you.
fine. Yeah. Okay, so the same property will occur. So if we combine these two, so this one and this one, if you combine, those two are also mutually exclusive and exhaustive event. All right, so let's do some practice.
For question 1, A is the answer, sir.
Yeah, it's correct.
Because
And
when
for
they are
question B,
independent, no element is common in them.
but there is nothing called about independence in the first question.
Sorry, mutual exclusive, sir. Sorry.
Yeah,
When they are mutually exclusive, no elements are common.
Yeah, fine.
Yes, sir.
And for B, question number 2.
Sir, for question number 2, option A is the answer, sir.
Yeah, it's correct. Okay, so we'll move on. We have one more question, or two, three questions coming up.
Answer is no, sir, per question. Answer
Okay.
is no, sir, first question.
Okay, next one. But can you think again? Why is it no or yes again?
Sir,
Why do
C,
you
sir,
say it is
answer
dependent?
0.8.
0.8.
So yeah, second question is C, but first question, it's no.
First
Why do
question.
you say it is and answer is no? Can you explain so that other class can also? Actually, the answer is yes.
Mutually exclusive means no elements are in common, sir. So there is no chance of dependency.
No, but you are wrong about your concept about dependency is wrong. So let me explain it again. So let's say again.
Sir,
Yeah.
may I speak, sir?
Yeah, please.
Yeah, sir. Rolling a dice is a separate event, sir, and
Hmm.
tossing a coin is separate event. These two are mutually exclusive, and one cannot depend on another.
How they are mutually exclusive? No, right?
Sorry, yes, sir, yes, sir. Please go on, sir.
So yeah, let me explain this. So let's take the example of tossing a coin. So we know that we are tossing the coin only once. Okay, so we can get head or tails. So once we get head, what is the probability of getting tail?
One by two,
So
sir.
1/2. 1/2.
yeah, but what is the probability of occurring that event?
0, sir.
0.
Yes, sir.
Okay, so it is dependent.
How can you say it is dependent, sir? Can you come again?
Yeah, I will explain it again.
Yeah, please.
Okay, so let's go with an example. Actually, so let's say one event occurred.
Yes,
One
sir.
mutually. So we have two events which are mutually exclusive.
Yeah, got it, sir. I got it. Thank you, sir. Go ahead.
Okay. So for others, so if one event
Sir,
occurs, it
sir, continue, sir. Continue, sir.
okay.
Sir,
So if
you need
if
explanation, sir. Yes.
okay, I will explain. So the correct answer is A. Okay, the yes is the correct answer. So the explanation is if one event has occurred in a mutually exclusive event, it completely eliminates the possibility of occurring the other event. So like if while rolling a die, if the event of getting even number has occurred, then it completely eliminates the occurrence of the event of getting odd numbers. So that we can say that if one event of getting even numbers has occurred, then the event of getting odd numbers will not occur. Do you get it?
Sir, got that point, sir. But what it is relevant to mutually exclusive, sir? If odd number occurs means even number will not occur. That is the probability. So I understand that. So how we can relate with mutually exclusive, sir?
So it's like mm, um, so let's take the example of writing an exam. So there is only two possible outcomes, that is pass or fail. Okay.
Yes, sir.
So if you have passed, you cannot fail.
Yes, sir.
Yeah. So the occurrence of one thing, like the occurrence of passing, changes the probability of the other event to 0. Still, maybe it's kind of so if you write, so let's say the independence. For independence, we need P of A intersection B has to be P of A into P of B. This has to be satisfied. Okay. Then for mutually exclusive, we have probability of A intersection B has to be 0. All right. Now, if you combine these two, okay, so now if you are combining, this is for independent and this is for mutually exclusive. Now, if you say here, if you combine these two, so we are trying to see if a mutually exclusive event can be independent. So if a mutually exclusive event is independent, this has to be satisfied. That is, probability of A into probability of B should be equal to 0. Right? So you agree with this up to this much? Do you agree?
Yes, sir. Yes, sir.
Okay. So
Yes.
let's say
So
our
here,
events that
what you are trying to explain here, sir, if one event is happened, so that is definitely reflect on another event. So that's why
yeah,
we are telling that is mutually independent, right, sir?
yeah.
Okay, sir. Thank you, sir.
Okay. So I will complete this explanation also. So for an exclusive event to be independent, this has to be satisfied. But uh, like our example, so probability of let A be the probability of getting what odd number, and B is probability of getting even number. And so both the probabilities, probability of A is greater than 0, and probability of B is also greater than 0. So if this is has to be satisfied, and this has to be satisfied for the exclusive event has to be independent, mathematically we can say that P of A into P of B will be greater than 0 from this for a mutually exclusive event. So this will contradict the independent what we can say independent condition, mathematical condition. So we have to, we will also it yeah. So that's the, so this is not correct. So the events are mathematically also we can show that the events are mutually dependent. And only one possibility is that if one of the event has 0 probability. So that is like a kind of a degenerate case. So we won't discuss such cases. So let's say our probability of getting 7 when rolling a die, it's 0. So if one of the event is defined like that, then this equation can be satisfied and an exclusive event can be independent. Only if one of the event has the probability 0. Okay, so we'll move on. We have the conditional probability coming up next. So what is conditional probability? So if two events A and B are not independent, then the information available about the outcome of an event A can influence the predictability of event B. So let's take this example. So this is the formula for conditional probability, and it is read as probability of B given A, which is probability of B if A has happened. So that is what this equation means. So the equation is P of A intersection B divided by P of A. Now let's explain it with an example. Okay, so we'll again draw the Venn diagram. Okay, so it will be easy. So our event A. So we are tossing two coins. Okay, so event A is first toss is head. First toss is head. So we have head, tail, then head and head, and we have other events like tail, head, and head, tail, head, and tail, tail. So these are the events that we have. Okay, so now our first question is, and we have two events A and B. B is two successive heads. Okay, so now let us try to calculate probability of B. That is probability of getting two successive heads. So probability of B, we know it's 1 by 4. We have only one case, that is so we have one case, that is probability of two successive heads. So we have head and head. So we have one case which gives two heads, and we have four number of elements in the sample space. So probability of B is 4. Now the conditional probability, we are asked what is the probability if the event A is given, then what is the probability of getting, what is the probability of event B happening? Now we know that event A has occurred. So now we are asked probability of B and A has happened. So once A has happened, so before A has happened, this was our sample space. We had four elements in the sample space. Now A has happened, which is the first toss is head. So once first toss head has happened, in the conditional probability view, this is the new sample space. So let's say new sample space. Again, since we are given a condition that A has happened, we have a new sample space, or the conditional probability gave a condition that restricts the sample space. Okay, so now the sample space is this small circle, and it has only two elements. Now what will be the probability of two heads? So inside this we have one element. So that makes our new conditional probability equal to 1 by 2. All right. Again, now let's try to use the formula and do the work. So this was from the Venn diagram. Now probability of A given B is equal to, what is the probability of A intersection B? That is the first toss is head and second toss is head. So that is 1 by 4. We have one element. Now, so in probability of A intersection B, there is no condition. So in the sample space, we have 4 elements. And probability of A, that is also having the full sample space. So we will again have 4 elements. And but in this case, probability of A is, we have 2 elements inside A. So it will be 2. Now let's give this into the formula. So we have probability of B given A is equal to 1 by 4 divided by 2 by 4, which will be again equal to 1 by 2. So the probability of getting two successive heads given the um, first toss is a head is 1/2, whereas if there is no condition given, it is 1/4. So that is the conditional probability. So if this concept is clear, you can answer these questions. Try to write the equation. Then, so here I will give a clue. So if you A intersection B is equal to P of A into P of B. So if you use this is the independence condition. So if you use this and try to solve it, please, you can answer the first question.
Option A, sir.
Option?
A, sir. A.
Okay. Yeah, that's the correct answer. And the second question? Let's try to formulate it. Is like person. So probability that a random certain person likes ice cream, given that they like chocolate. So the equation will be P of I intersection C divided by P of C, right? Yeah. First,
2/3,
right,
sir.
2/3, yeah, correct. So if you use this P of I, so from this we can say P of I is 0.4, and P of C is how much? 0.3, and P of I intersection or C intersection I will be equal to 0.2. So from this, if we substitute, we can get the answer. Okay, now we have seen different examples like head, tail, 1, 2, 3. In case of a die, in case of a coin, then all those examples we have seen. So why we need a random variable? So random variable actually maps a sample space to real number line. So whenever we deal with these problems in computers and all, we cannot actually use like head, tail, and all those things. So we have to give numbers. We have to use numbers in if you are dealing with computers, and in data science also we need only numbers. So the random variables will map these sample space into number line. So we have discussed discrete probability as well as continuous probabilities. So we have discrete random variable. So that takes one value from the discrete set of values. So like rolling a die. So it's already in numbers, the rolling a die. So we can easily connect to that. Then continuous random variable can take value, any value in the number line. So try to quickly answer these questions. So which of the following is an example of a discrete random variable?
ಎರಡು ಬಿಸ್ಕೆಟ್ ಅವೆ ಎರಡು ಯಾವತ್ತು ಗೊತ್ತಿಟ್ಕೊಂಡು ಇಷ್ಟ
C, sir.
Yeah, C is the answer. Then for the second one, random distribution of a discrete random variable must satisfy which of the following?
Sir, B is the answer, sir, for second question.
Yeah, it's a correct answer. Okay, so moving on. So we will define probability mass and probability density function. Probability mass or probability density function. So it is the function that helps us to assign values or the real values between 0 and 1 to every outcome of a sample space. The probability mass function use discrete random variable so that we can use the values like the direct values to the random variable. So like in the example of tossing a coin, so let 0 be the probability of getting head and we give 1 as tail. So the probability of getting head is 0.5 and probability of getting tail is also 0.5. Coming to probability density function, it uses its continuous in nature so that it cannot be defined as a single value as we have discussed in the previous slide. So like the example on a number line. So always it is defined from a between two numbers or limits. So this should be okay. So this is actually integral a to b f of x dx. Okay, so we cannot it should be temperature. Okay, temperature between 20 and 40 degrees centigrade. So what is the probability of having the temperature between 20 and 40 degrees centigrade? Okay, so these are the functions which give probability values to the random variable. Now, do you want the answer? So the box contains 20 defective items and 80 non-defective items. So let's say we have 20 defective and 80 non-defective. If two items were selected at random without replacement, remember without replacement, what will be the probability that both items are defective? So don't think about conditional probability and all those things now. So just try to answer. So both items need to be defective. So in the first row, we need to take 20, any 20 items from the total 100. And now we have only 19 defective items left. We are doing it without replacement and we have only 99 items left. So if you do this, how much it will be? 5, 21 by 5. So it should be, answer should be D, right? Okay. Okay. So let's see binomial distribution. Okay, so let's see some distributions. So we will discuss binomial distribution first, then we have the Gaussian distribution. So binomial distribution, so I think there is something missing in the graph. I will try to draw it. Okay, so here let me see if I can get the correct figure. Okay, so it will be something like this, right? So if the head bias is high, so if we manipulate the coin to always give head, so that the probability of getting heads will be 1. Then if the coin is fair coin, we'll have the probability of head will be 0.5. So let's see what this equation, binomial distribution equation, how does it come? So let's take the example of tossing a coin itself. So our aim is to find, so we toss the coin like maybe 50 or 20 times. So we toss the coin 20 times, or maybe how much it is, I don't know. So we are trying to toss the coin 20 times, and we want to find out how many times it has succeeded in our event. So let's say our event is getting a head. So we have head here, head here, head here, then tail, head, and so on. We'll have. So finally, we need our event. Let's say we need 5 heads and 15 tails. What is the probability of getting this event? So one way to do this is we can calculate how overall we can keep the 5 heads and 15 tails in this 20. So the probability of getting head is 1 by 5, 1 by 2. The probability of getting tail is also 1 by 2. So if we n is the number of trials, so in here the n is 20. Then we have x is the number of successes desired. So let's say our event is only 5 heads. So let's say our 5 is the x. Now probability of getting a success in one trial, that is probability of getting head in one trial, that is 1 by 2. Then q is the probability of getting failure. In this case, it is also 1 by 2. But so let's say we are taking the example of die, and our decide succeed is getting number 1. So in that case, p will be 1 by 6 and q will be 5 by 6. So it can change. Now, how does so we know this how this one comes, right? So it is just 1 by 2 raised to number of successes and 1 by 2 raised to number of failures. N is 20 by minus 15, 20 minus 5, that will be 15. So we know how this term comes. So why do we need this term in case of a binomial or in case of the probability? Since we have 20 spaces here, 20 spaces are here, and we need to know in how many ways we can get these 5 heads. So maybe in the first 5 trials itself, we got the 5 heads, and in the remaining we didn't get. Or we got the tail in the first 5, and the next not a tail in the first 15, and the last we got 5 heads. So there are a lot of possibilities of getting success. So this is the combination, or from permutation and combination you might have studied how in how many ways we can arrange this h and t so that this entire thing will have 5h and 15t. So that is how we got n factorial by n minus x factorial divided by x factorial. So that is the complete formula of binomial distribution. So it's the formula is used to find how the probability of success in say n number of trials, x number of success in n number of trials. Now coming to continuous distribution, we cannot know the exact number of probability like we have defined now for the binomial case. So it's always in a range. So that's where we use the Gaussian or normal distribution, where we have the mean, mu is the mean, and sigma is the standard deviation. So this is the formula of a normal or Gaussian distribution. So always we have to remember in Gaussian distribution, the probability will be given from a range. So we'll see how we'll find that. Then we have a chi-square distribution. So this is just characterized by one parameter, that is the number of freedoms k, and it is actually got by squaring the normal distributions. So few questions. Yeah. So what types of
Option
events
B,
does
discrete
the
events, sir.
okay, and for the second question,
Bell shaped, sir. Bell shaped. Option C.
yeah, yes. Okay, so then the next set of questions, come on. Chi-squared, we use the degree of freedoms only. So for the next one, I will give the, so from this figure, if you can figure out, it will be good. So what percentage of data falls within one standard deviation of the mean in a normal distribution? Approximately, if you can say, if you can see the figure, and I think the figure is not visible. Okay, now it's visible. Okay. So from the figure, so here we have the mean, then sigma is the standard deviation. So within one standard deviation, what percentage of data will be there? So just looking at the figure, if you can figure it out, please.
50%, sir.
20. See, this is one standard deviation. This is another standard. So within this range of how much will be there? It's already written.
60%. Yes.
Yeah, it will be 68%. Okay.
Excuse me, sir.
Now,
Will
yeah,
you please
please.
explain chi-square
What?
chi-square distribution?
Chi-square distribution.
Yes.
Okay. So chi-square distribution is actually defined by only one variable, that is the degree of freedom it has. That is the denoted by the k. So it is actually got by squaring, adding too many normal distributions. So we have the independent standard normal distribution that we square and add, that will end up in chi-square distribution. So you need not by heart this formula, and because it comes with the gamma function. This is the gamma function, and this is like in problems and all, it won't be asked much. So even if you want to directly get a value like from the normal distribution and all, it is not possible with chi-square distribution, because finding the value of gamma function and all is difficult. And one thing to let's say, so if somebody asks some of the characteristics of chi-square distribution, so we can say it depends on the number of degrees of freedom. That is it actually denotes the number of squared standard normal variables that have been added. Then it's always like skewed to right or left. And whenever we increase the k to higher number, we can approximate it to be symmetric with the mean, symmetric with the mean. Actually, this chi-square distribution is not much popular. It's popular, but in academics, we will be dealing mostly with the problems concerning binomial and normal distribution. It is mainly used for hypothesis testing and all. So we'll see hypothesis testing today. So yeah, we'll see that. Before moving to hypothesis testing, we'll see some of the terminologies, that is expected value. So expected value is nothing but the mean value or the average value. So if you repeat some experiments, what we get, what we expect. So the probability of getting ahead. So if we repeat the experiment a number of times, now let's say if we repeat once, the probability of getting heads, it can be. So we are doing this experiment like we are counting the number of heads, and this is the number of heads divided by total number of trials. So maybe in the first attempt itself we got an head, so that the probability is high. In the second attempts also we got head, so it will be 2 by 2. Again it is high. Then on increasing the number, we get one tail, so it will be 2 by 3. Then it can go up to so the number below the denominator will increase, and depending upon the number of heads or number of tails, the numerator can increase or being stagnant. But if we repeat the experiment a number of times, we are not certain if it is fair coin. The highest probability will be that and it will end up like some 250 by 500. So the 500, if the 500 is an optimal number of trials, then 250 times we are expected to get hit. So in a few frequentist approach, we will get 0.5 as a probability of it. So that is the discrete case. Now coming to continuous formulation, we will take this example. So this is the formula for continuous distribution. So the summation will be replaced with integral. So usually mu is used to denote the expectation, and variance is a quantity which denotes how the data are distributed with respect to mean. How variant is the data. So let's say if we are taking so let's say we are interested in calculating the height. So the height, we took the measurement of the height of the people from America, US, so that compared to Indians, they will be higher. So their mean will be higher, and so let's say their height ranges from 5.8 to 6.2, and they have a mean 6. And let's see their variance is let's say 0.2, 0.2. Now, if we add other world populations into it, so we add less, let's say we add Chinese people or who are not much much height. So let's say we add some people. So it came down to 5.5. And also we had people who are more higher than Americans. So I don't know which country will have those. So it will be 6.5. Now see, the variance has increased. Even though the means stays at 6, the variance or the variability in the data has increased. So it will be 0.5 here and 0.5. So that is the variance. This is actually standard deviation, and variance is the square root of that. Not square root, square of that. So variance is calculated by using the same formula for the expectation, but inside we'll take the mean and subtract from each of the individual measurements. So if you roll a fair 6-sided die, what is the expected value of a single roll? You can use the formula. P of x. X takes the x is the random variable value. So it ranges from 1 to 6. I'll start. It will be 1 into 1 by 6, then plus 2 into 1 by 6 plus so on to 6 into 1 by 6. So if you do the calculation, finally we are going to get 1 plus 2 plus 3 plus 4 plus 5 plus 6 by 6. So that will
3.5.
be 3.5. Okay. And in the second question, in a normal distribution, where is the expected value located? We haven't discussed mode, median, and all. So it will be at the mean. Expected value is the mean of the distribution. Okay. Now we will see some properties of the expected values. That is, if we have only one variable, then we can expected value of a constant is always the same. So that so if a is not a random variable, say a is a constant, then expected value of a is a. Then on multiplying a random variable with constant and taking the expected value, it is nothing but the constant value into expected value. So these are the two equations. But coming to variance, if we are taking the variance of a constant value, that will be 0. So variance of a constant is equal to 0. And the variance of a random variable multiplied by any constant will be a square. Constant will be squared, and the variance of the random variable. And also, if you have two random variables, we'll have to find the covariance also. So quick questions. So variance of x is given as 9, then variance of y is given as 16. So what is the variance of 2x minus 3y? And it is given x and y are independent. So if it is independent, covariance of x and y will be equal to 0. Remember, you have to square the constants in case of variance and try to give me the answer.
Be 2 square into variance of x plus minus 3 square into variance of y. Am I correct, sir?
Whatever you said is correct, but yeah, try to calculate and give me the answer.
But the value I'm getting it a negative value, sir. That's what my doubt is.
So whatever you said is correct. What can you say it again? What you said?
Yeah, that is 2 square into variance of x.
Okay.
Minus 3 square into variance of y.
But there is a plus here. Then minus 3 square.
Okay, minus 3 whole
into
square.
variance.
Yes, sir. Yes, yes, yes.
Yeah, okay. So was that equation correct? See, here it is always plus. The variance is always plus. We have to do the square of the coefficient, but it is not applicable when you find the expectation. So now try to answer. So it's
The
already
answer
given.
is 180, sir.
Yeah, 180. And for the second case, you can actually consider the negative. So it will
Sir,
be one.
one is the answer, sir.
Yeah, one is the answer. Yeah, correct. So yeah. So we'll just see what is covariance and correlation. So covariance indicates the direction of linear relationship between the variables. Those are not standardized values, and value can be anything. So it is like how the if two random variables are related to each other. So for that, the formula is okay. So formula is x minus the mean of that variable into y minus the mean of that variable divided by n. And for correlation, so correlation says that for it calculate measures the strength and direction of the linear relation between two variables. So correlations are standardized values. That is, the values of the correlations always ranges from -1 to 1. So what is -1 to 1 indicates? So let's say um, if one variable increase, then the other variable decrease. So that makes both are negatively correlated. Okay, so um, if you study for an exam, the number of hours, most of the time, in most of the cases, the number of hours will be directly proportional to the marks. So if we take two random variables, so getting the marks and get time of the study, those will be highly correlated, and they both will have positive correlation. And if you uh, change the number of hours you spend to study into number of hours you spend in social media, then that number of hours and the marks obtained can be highly negatively correlated. Okay, so some properties of joint probability density function. Here we have some integrals. So if you have two random variables x and y, then their joint probability density function will be given by the integrals. So minus infinity to a is for x, and minus infinity to b is the limit for y. Then covariance, we can find the covariance by the expectation formula. So these equations are for this equation is for the discrete case. Now in case of continuous case, we will have to use this formula, expectation of x minus mu x, which is the mean of the x, then the mean of the y.
Sir,
And
what
the
is the
correlate
symbol before integration, sir?
that is some kind of typo error. Don't consider this. The
It's okay,
equation
sir.
is
It's okay.
okay, yeah. Minus infinity b minus infinity a. Okay. Okay, so we are running out of time, so we'll have a few more questions. So if two random variables are independent, what can we say about their covariance and the correlation? If they are independent, so what can you say? So if it is independent, there is no covariance will be equal to 0, as we have seen in one of the problems before. And if it is independent, if one thing happens, it cannot affect the other variable. So the correlation is also equal to 0. The correlation coefficient between x and y is 0.6, and the covariance between them is 25. Then find the product between variance of both the variables. So again, I'm giving the formula. So the covariance, okay, correlation is given. So correlation between x and y is equal to covariance divided by the variance of x into variance of y. So substitute the values and you can find the answer. So it will be, this is given as 0.6. This is given as 25. So the answer will be 25 by 0.6. So it will come to be 41.6. Okay, so these are some of the commands that you can use in R Studio to calculate the probability. So here the probability of this is the normal distribution. Then you can use the chi-squared or binomial or uniform. So here you have to give the value x, then mean and standard deviation of the normal distribution or whatever distribution that you want to give. Then lower tail is equal to true or false. So that means, so you have seen this normal distribution table. So here we have some mu here. So if the lower tail is given as true, it will calculate the probability of occurrence. So let's say we have given our x here. So that will calculate this probability or this area. So another way to think of calculating the probability in such a uniform distributions is like, so if this is area A1 and this entire area is A2, then the probability is A1 by A2. In case of standard normal distribution, where mu is equal to 0 and standard deviation is equal to 1 or variance is equal to 1, this A2, the entire area will be equal to 1. So that finding only this area will give you the probability. Now, if lower tail is given as true, this is the area that it is going to find. If lower tail is given as false, this is the area that is going to be calculated. Now, Q norm is used. This Q norm or Q chi-square, Q binomial, Q uniform is used. So let's say we are given this probability value. So let's say it's 0.4, and we are asked to find this x. So in such cases, we can use this Q norm, where we will give the probability value, mean and standard deviation of the distribution, and we will say if this probability is lower tail or upper tail, and it will give this value as output. In P norm, we are giving this value and getting the probability output. In Q norm, we are trying to get the value from the probability. So now we are coming to the last part of today's lecture, that is sampling or statistical sampling. So population is a set of all possible outcomes of random experiment. Then sample set is a limited number of or finite set of observation from that population that we take. So why do we need this sampling techniques? So sampling helps to make inferences about the population, because and the inference can be uncertain because sample might be uncertain. So again, going back to our old example of height. So if somebody asks what is the height of the world population, and if you are sampling only from USA, the we are asked what is the mean height of the population of the world. And we are sampling entirely from USA, so it will say that the mean height is higher. Then if we add or if we choose our sample from the entire world, then we will get a more real world figure. So that is the uncertainty that can happen if the sampling is also uncertain. Even during elections and all, we see these exit poll results. So that is also sampling. So in elections, it's not possible that these agencies who conduct these exit polls can get the correct details from all the population, all those who have voted. But what they will do is they will ask a few people about their opinion, and they finally makes a statement. Even that can go wrong. There are cases like that. So it's all the surveys and everything is all are statistical methods. So in statistical analysis, we have the descriptive analysis, like we can plot the graphs. So plotting the graphs like histograms. Histograms are very popular. So if you say we have, I will take the example that was discussed in the video lectures. So we are trying to find the height of a tree. So we have a lot of values like, so if this is the entire sample, we have 55, 55, then 56, 60, 71, 72, up to, let's say we have up to 80. So in graphical method, what we do is we'll make bins, or let's say this is 55, 60, 65, then 70 up to 75, 80. And if we'll count the number of trees which are falling between 55 and 60. So let's say we have 1, 2, 3, 4 here. So this is number 4. Then between this, we might have another number 5. Then we'll have 6 numbers. On counting, we'll get to plot different kinds of plots. So this is one of the histograms that we see in most of the times. So even when we plot the histograms, we can see that most of the time, higher number of occurrence will be in the middle part. So if we increase our number, if you take n is equal to 20, then if we increase that to n is equal to, let's say 1000, we might end up getting some curve which is very much similar to normal distribution. So normal distribution is a naturally occurring process. So in most of the cases, we will see that. So it happens because both the extremes will be very less numbers. So let's say a person having height greater than 7 feet, like if you talk about in Indian circumstances, that will be very less. Similarly, the person having height less than 3 feet and everything will be, that also will be very less. If you take the sample or the population or consider population, only the adult population is considered. Then we have the numerical analysis, that is summarizing the sample set with the mean, variance, all those single values. So we cannot go on and tell. So if we take all these values, we cannot go on tell the data we have is 55, 55, 56, 70. We cannot tell all these 100, 1,000 values to everyone. So what we do is we will calculate the mean and variance of the data, and we'll just even though we'll assume that the data is from a normal distribution, and we will apply those formula, or we use the statistical methods to calculate the mean and variance from the data, and we report only that. Then we have the estimation parameters of the probability density functions and the hypothesis testing. So we'll see the hypothesis testing now. So these were some of the plots that we can make. We can make the scatter plot, histogram, box plot. So box plot, we'll have the, we'll clearly see the outliers also. So most of the data will be in this area where we'll have the median here. Then the outliers will be on the both extremes. So these quartiles are like This is 0. So this is 25%. Then we have 50%, 75%, and 100%. So what this quartiles means is like the 50% of data is below this, and we'll have 25% of data between these two, and similarly on the upper side also. So these are the numerical statistics that we're talking about. Different that is mean. Mean is the mean value of the total sample. Then median is the middle value. Then mode is the most frequent values. So one thing about mean is, so let's say we have this example, so 1, 3, 4, 6, 6, 7, 8. So in all the cases, this is the same example, same numbers. But let's say when calculating mean, somehow instead of 8, we did entered 18. We know 18 is an outlier when we look at this data. Now we calculate the mean again. So what will be the mean if we add 18 instead of 8? So it will be 45 by 7. 45 by 7. So what is the value 45 by 7? It will be around 6.5 or something. Okay, let's say it's around 6.5. Let me calculate 45 by 7. It's actually 6.42. Okay. So now we see that the mean has changed from 5 to 6.42 because of an outlier. Now we are coming to see the median. So median, instead of 8, we are writing 18. So still the middle element is say 6. So there is no change in the median. Similarly, for the mode also, there will be less change if we have outliers. So, but mean, all these values are used. So if we are doubtful that our data is more prone to outliers, we can use the median. Okay, then now coming to hypothesis testing.
Sir, excuse me, sir.
Yeah.
Sir, while you are calculating the median, we have taken odd number of events, odd number of values.
Okay. Okay.
Median
So if you have
35, even number of values, sir.
So if you have even numbers, so let's say we have 1, 3, 4, 6, 6, 7. So this is even number. So
Yes,
in this
sir.
case, we'll take two elements and take the average. So in this case, it will be 4 plus 6 by 2. It will be 5. 5 is the median.
Right, sir. Okay, sir. Thank you.
Okay. Yeah. Okay. So even in mode, so let's say we have 1, 3, 6, 6, 7. So now if we have 1, 3, 4, 6, 6, 7, 7. So if we have two frequently occurring values, so it will be like a multi-mode or bi-mode, something we'll call. I'm not very sure. You can see, you can search it in somewhere and see. There is some term bi-mode or multi-mode something. Okay, now hypothesis testing. Hypothesis testings are used to make decisions. So like, should we invest in some company stocks or some other decision if we want to make, we use the hypothesis testing. So like whether the effect of drug A is similar to drug B, and all those can be calculated by hypothesis testing. So in hypothesis testing, we have two types of tests mainly, that is two-tailed and one-tailed test. So let's say we are, and also we have two hypotheses. This is the null hypothesis and alternate hypothesis. So this is null hypothesis. This is alternate hypothesis. So why we need two hypotheses? So we are trying to say that our hypothesis is wrong based on the conditions that we make. So first, let's see what is null hypothesis, null and alternate hypothesis. So we are making two statements. That is, application of biofertilizer X increases the plant growth. So that is the alternate hypothesis H1. And the null hypothesis is application of biofertilizer X do not increase the plant growth. So the alternate hypothesis is a hypothesis which serves the researchers trying to prove or we are trying to nullify our null hypothesis based on the data we have. So we'll see what this is based on the some examples we'll see, so it will be clear. So coming to two-tailed and one-tailed test. So two-tailed test occurs when we say that this mean kind of hypothesis is not equal to whatever the mean that we have said. So let's say again coming to height. So we say the height of a mean person in India is around 5.8 feet. So we just need to prove the mean is not 5.8 feet. So in such cases we use two-tailed hypothesis. And in for one-tailed we say the height of a person is not less than 5.8 feet. So in that case, we have to prove the other way. So if we say the height, or in this example itself, so if we say some mean value is greater than 23, we have to just prove that the mean value is less than 23. Whereas, so even if it comes as the mean value is whatever higher hypothesis, the mean value is greater than 23, then we will have to accept our null hypothesis. Whereas if we say the mean value is 23 and it is not, and if you want to just prove it is not equal to 23, we can use the two-tailed test. We'll see the examples, so it will be more clear. So, okay. So a teacher claims that the mean score of students in his class is greater than 82 with a standard deviation of 20. So if a sample of 81 students are selected with a mean score of 90, so before that I need to give the equations needed. So we have two types of tests, that is Z test and T test. So Z test is used when population variance is known. Then it is usually used when the sample size is greater than 30, and it is based on normal distribution. So this equation is x minus mu divided by the non-standard deviation by root n. N is the number of population size. Whereas T test is used when the sample size is less than 30. It also has the similar equation, x minus mu divided by s by root n. So this mu is the what we say, the hypothesis that we give. Then x bar is the sample mean that we calculate, and S is the sample standard deviation that we calculate, and N is the size of the sample. Now coming to the questions. So a teacher claims that the mean score is greater than 82 with a standard deviation of 20. Then sample size is 81, so we can use Z test. And in the sample test, we have selected with a mean score of 90. Then we have to see if there is enough evidence to support this claim at 0.05 significance level. So the solution goes like this. So we have 81 students, that is n is equal to 80. Then sample mean. So sample mean is given as x bar is equal to 90. Standard deviation is also given. Population standard deviation is given as 20. Our hypothesis is the teacher claims that the mean score is greater than 80. So that is the alternate hypothesis that we have to 82 that we have to prove. Now we use the formula that is x bar minus mu divided by sigma by root n. So if we do this, we are going to get a value 3.6. Now how to use this value to finally get a conclusive remark? So if we look at the normal distribution table, it is given. So this is a single tail test. Okay, it is given the significance level is 0.05. So what we can do is using Q norm. If we give the Q norm and give the value, so if it is significant level is given as 0.05, that means it is 5% here, and here we will have 95%. So in the Q norm, if you give 0.95, we will get the value for the standard normal table, that is 1.645. Now, if it was two-tailed and it is given the significance level of 5%, we will have to find. So this is for two-tailed. Okay, so two-tailed. So in case of two-tailed, the 5% has to be split into upper tail and lower tail. So you will have 2.5% here, 2.5% here. So the value that we will have to find using this Q norm will be equal to how much? 97.5 or 0.975. So that we will get this value. Now in this problem, our Z value came to be 3.6 and our critical value is 1.645. So since 3.6 is higher than, or 3.6 lies in this area, it's higher than this 1.6, we can say that we can reject our null hypothesis and accept the alternate hypothesis. That is, we can say that, or the teacher's claim is correct. That is the alternate hypothesis that the average mean score of the students in the class is greater than 82 can be accepted. We'll see one more problem. So a researcher wants to test whether the mean weight of a sample of 50 apples in the is significantly different from a claimed population mean weight of 150 grams. The sample mean weight is 149 and the sample standard deviation is also given. Okay, so calculate the t statistics for this test. So you will be wondering why we are using t statistics even with 50 number of apples. We already said that the sample size has to be less than 30, but in this case the population variance or population standard deviation is not given. So in such cases we have to use the t-test. So coming to the solution, we find the t statistics. So here the number of apples n is equal to 50. Then we have to find the in t statistics for using the t statistics table, or in the equations in R, we will have to find the degree of freedom. That will be the total number of sample divided minus 1. Then we have the population mean given, then sample mean given, and sample standard deviation. If it was population standard deviation, we could have used the Z test, but here we have to use the t test. Then we have H naught, which is the null hypothesis, and we have the H1, which is the alternate hypothesis. So in this example, this is a two-tailed test. Okay, because the researcher just want to see if the mean or the sample mean weight of the sample is different from the weight of the population weight. So he does not want to see if it is higher or lower. He does not want that. In the previous example, the teacher claimed that the marks were mean score was higher than the population mean. Okay, so no, yeah, mean greater than the population mean. But in this case, he just want to see if it is lower or higher, not or it deviates much from the population mean. So in this case, we use the two-tailed test. So the equation again is x minus mu, and we get the value minus 0.071. So now in this example, the confidence interval is not given. It should be 0.10 because it is 5% here and 5% here, because this t value corresponds to that. Now we have I'm not very sure about that. So I'll have to confirm these values. Okay. So anyway, it is a two-tailed test, and finally the value is 0.7071, and the critical value is plus 1.676 and minus 1.676. So if the calculator value was in this range, we can say we can accept the alternate hypothesis. But since the calculator value is within the range, we will have to stand by the null hypothesis. That is, null hypothesis is not rejected. Null hypothesis has to be accepted in this case, because the calculator value is within this range. It's not outside of the critical value. So in such cases, we can say that, or in this case, we can say that the mean of the sampled 50 apples is not significantly different from the mean weight of 150 grams, the mean weight of the population weight. Now we have a summary of the test that can be used. So you can just read the characteristics example applications. So mostly these two tests are enough. These tests are also popular in statistics. Okay, so if you have any questions, please you can go ahead, or else we can meet next week.
Okay, sir. As of now, no questions. Thank you for the session.
Okay, thank you. Yeah, thank you for joining. Okay, thank you.
From my side.
Right. So if you have any question, you can make.
Sir, I have a question, sir, regarding that population and sample space.
Okay.
In our undergraduation, what we learned is sample space is the total number of outcomes that are expected.
Okay, yeah.
And now you said it is only a finite set of outcomes.
No, it's a finite set of all outcomes in case of a discrete case, but in case of continuous case, it will be an infinite uncountable set.
Then I didn't get the difference between the word population and sample space, sir. Can you elaborate that, please?
Population and okay, so don't mix the probability part with the what we say statistics, the terminologies. So population is the entire population that we have, and the sample is a finite number of. So let me go back. So here, okay. So population is kind of like a. So let's say, let's go back to the height experiment itself. So if we need to get a very high accurate results, we need to ask each and every population of the world to get the height. But that is the set of all possible outcomes. So sorry. Okay. So that is the set of all possible outcomes. That is asking the height of each and every individual and calculate the mean. Since that is not possible, what we do in statistics is we choose people at random from each group. That is independently we will choose, and we have to choose such a way that all the variances or the variance that we can expect in population is captured. That's why don't confuse this sample set with the sample set of probability. That is sample space. This is sample set. Consider it like that. Then it will
Yeah,
be.
I got it, sir. I got it. Thank you.
Okay, then see you. Good night. We'll meet on next week. Thank you.
Good night, sir. Thank you.